Hello students, in this video we covered the topic sums of random variables. Overall this week we're talking about functions of random variables, but now here this is an important special case where the function we want to understand is simply the sum. So we're going to see, we're going to define a new random variable S to be simply the sum x1 plus x2 plus a certain number, let's say n, of random variables. And so here you could call this h function, h of all those random variables, the function being simply their sum. Now, we already know that if those random variables are independent, then the moment generating function of their sum s is simply the product of the individual moment generating functions. So if we can compute this thing and then recognize the expression as being the MGF of a known distribution, that's a win. So we've already solved the problem of finding the distribution of this S because we've computed its MGF. We recognize it as being that of a distribution we know, and that's it. We're done because we know that the MGF uniquely identifies a distribution. Now, just to make this idea a bit more concrete, let's give a simple classic example of this. So you might already know that the sum of independent exponentials with parameter lambda is a gamma, with the first parameter n, the number of exponentials you're summing, and the second parameter, the same lambda. So, and we can see that very easily with this MGF technique. So if I go here, this is just the slides about the different distributions. So let's look at the MGF of an exponential. It is this simple expression. So recall the MGF is a function of the argument here called t, and then lambda is the rate parameter of the exponential. But now imagine that you're summing, imagine that S is the sum of n independent exponentials, okay, each with this MGF. Well, then you know that the MGF of S will be, let's call this MS of t. You know that's going to be this times this times this times this n times. So of course it's going to be lambda over lambda minus t to the power n. Right? You're just multiplying with each other n times the same MGF because all those x's are assumed to have the same distribution. But now look at this. This is the MGF of a gamma where the first parameter is n and the second parameter is, of course, lambda. Okay, you don't believe me? Well, let's just go to the next slide talking about the gamma, and here you have it. The MGF of a gamma is indeed this lambda over lambda minus t to the power of this parameter. But so, of course, in our case, we have that this parameter is this n. Okay, so you conclude that because this is the MGF of the sum of those exponentials, you recognize that it's a gamma with specifically the parameter alpha being equal to n, and then the other parameter being just the lambda, the same lambda as in the initial exponential, okay, which I should put in green to be consistent. Okay, so just an example of what I mean here when I say use this trick to compute the MGF of this sum. If you recognize it as being that of a distribution you know, you're done. But the point, of course, is that this only works in a few special cases. You know, the sum of independent Poisson is again a Poisson. The sum of exponentials is a gamma. The sum of normals is again a normal, of course, if they're independent. You have a few special cases like that are nice, but in general, this approach will not work because you'll just compute this, you'll compute the MGF, and you won't be able to recognize it as that of a distribution you know. So when this approach fails, you should not despair. You can use a method called direct convolution, and this is what we explain in the next few slides. Okay, to obtain the distribution of S, the sum. So let's first have a look at this in the discrete case, but we'll see that the continuous case is completely analogous. So consider for now that you have a random variable, which we're going to call S2. S2 just to mean that we're summing two things. In this case, this is just notation we've chosen, but we're summing a certain random variable x and another random variable y. Now, the assumption we make is that those are discrete random variables, but more specifically, they take values in the integers, okay, which is not too restrictive an assumption. the Poisson, the binomial, the negative binomial, they all take integers values. And we assume here that those x and y are independent. Now, if that's the case, you can obtain explicitly the probability mass function of S2 and the CDF of S2 using those formulas. So here, this little s is just the argument. Okay, so it's just any value in the integers. By the way, this notation z, it means the set of all integers, including the negative one. So this z would be, well, it starts at minus infinity, but let's just say blah blah blah, and then -3, -2, -1, 0, 1, 2, 3, blah blah blah. I think you see what I mean. The set of all integers, including the negative ones. So for s in the integers, you get the probability that S2 takes the specific value little s by this sum. Now, what is this sum? You're summing all the cases where the sum of x and y will be equal to s. Well, yes, because let's for a second, let's forget about the sum. Let's look at what is there. If x equals k and y equals s minus k, well, their sum will be equal to s. Well, of course, x plus y, if x is k and y is s minus k, of course, you obtain s. But now it's not sufficient to just consider the case for a specific k. You need to sum all those probabilities. In fact, this is an application of the law of total probability, and this is explained a bit more in the next slide. But just conceptually, if x takes a specific value k, and if y takes the specific value s minus k, then their sum will be equal to s. But that's a specific k. If you sum for all possible k, if you sum those probabilities, you will get the total probability that S2 equals the specific value little s. But let's see that slightly more rigorously in the next slide. But let's just cover the second formula here. It's the same thing, but for the CDF, right? For the probability that S2 is smaller than a given value little s. Same thing. You sum over all the possible k's. You sum what? Well, the probability that x equals the value k, but now the probability, careful, that y is smaller or equal to s minus k. And again, this should make some sense because think about it. If you know x equals exactly k, but y is smaller or equal to s minus k, then you know that x plus y will be smaller or equal to this plus this. Well, smaller or equal to s, then little s. Now, let's present the proof, a slightly more rigorous proof of this formula, but the proof for this formula would be exactly the same. You would just replace inequality by an inequality. Okay, so let's see the proof for that statement. Okay, again, what I said is you use a law of total probability. You have a probability here. You could call this an unconditional probability. Now you can always write an unconditional probability by summing all the cases when you condition on an event whose intersection spans all the sample space. This maybe I should write. Well, I think you know what the law of total probability is, but let me just write it explicitly in the usual notation. You know, if you want a probability that an event A happens, you can always find it by summing probability that A given, let's call this event I, times probability of event EI. Okay, and here you would sum over all the i's. But provided, of course, that all those EIs, they are mutually exclusive, and their intersection is the whole sample space. But here, because I'm summing over all the possible k's, that's the case. That you know, x equals k for all the possible k's is indeed a partition of the sample space. Okay, hopefully that's clear enough. Now, the rest is just relatively simple manipulation, right? From here, from the first time to the second, here we are conditioning, right? So we assume we know x equals k. Well, so here, well, here we've just replaced S2 by what it is, x plus I. But then here in from second line to the third, we've simply replaced, okay, because we know x equal k, we replace here x by k, and then we rearrange, so we obtain y smaller equal to s minus k. And then what happens here? We have probability that y is smaller than whatever, given x equals k. But y and x are independent, or assumed independent here. So this conditioning here doesn't play any role anymore. So you can just rewrite that, well, this thing is just the probability that y is smaller than s minus k. Again, because of independence. And then you're done. Then this is exactly the formula we had the slide before, this formula here. And what I said is that this is proven in exactly the same manner. It's just that here you have an equality instead of an inequality. So in this proof, just replace the inequality here by a equality, and you obtain what you need. Here, and this last one would be provided y exactly equals s minus k. So you can call this the py s minus k, which is what we have here, provided that y equals exactly s minus k. So that's for the proof. And then do we have an example? Well, first a comment and then an example to try to make this slightly more concrete. And actually, just one more comment is that maybe we should make clear what we mean by all k here. By all k, we really just mean all k such that those probabilities are not zero, right? It serves no purpose to plug here some k's for which those probabilities are going to be zero, because of course, if this probability is zero or if this probability is zero, it's not going to affect in any way the sum. So with all k here, we mean all the k's for which those terms, when you sum them, they add something non-zero to the sum. And this should be a bit more clear when we review a specific example. So now just a comment that we've done this to find the distribution, either the probability mass function or the CDF, of the sum of two random variables, okay, which we call S2. But this technique, at least in principle, you can then iterate it and then find the distribution of the sum of any number of discrete random variables, which is what is said here. For example, let's say that you want to find the distribution of S3, which is the sum of three random variables. Note the following: you can rewrite your S3 in the following way. S3 is S2, which is over there, what we call x plus y, then plus the third element here called z. And that makes sense because why do you do that? Well, S2 you were already able to find its distribution here, and now you've transformed your sum of three things by the sum of two things, z plus S2. So you use again the same technique, and now because you found in the previous step the distribution of S2, you can find the distribution of S3, which is because you've written it as the sum of two things rather than three things. Okay, and so hence you can apply the same formula as before to find the PMF at CDF of your S3. Okay, now you see, before here we had x plus y. Now we have z plus S2. So z plays the role of x, and S2 plays the role of the y. Okay, but other than that, it's the same formula. Probability that S3 equals whatever little argument little s will be the sum over all the cases of z equal k times probability that S2 equals s minus k. Hopefully that's clear enough. You just use the same technique again, and then you could keep going. You could find the distribution of S4 it's now it's going to be S3 plus whatever the fourth term you add. I don't know how to call this, but let's say W. That is to say, once we know how to find the distribution of a sum of two independent random variables, we can, in principle, derive the distribution of an arbitrary number of independent random variables iteratively. Find the distribution of S2, then the distribution of S3, then the distribution of S4, distribution of S5, and so on. You keep going until you find the distribution of Sn, whatever n is in your specific context. Now, I say in principle because this approach gets cumbersome really fast. You might find S2 and it's already a complicated thing. Then you apply the method to find S3 and it's a super complicated thing. And then already there, it becomes very intractable to find S4, S5, etc. And so let's say an example that is actually not that bad, but already for a simple example, you'll see that finding S3 requires quite some work. Okay, the example is this. Suppose that xi is a geometric p, and those xi are independent random variables. We want to find here S3 by using the method we just presented. Now here they tell you use direct convolution. So use those formulas. You are forbidden to cheat by using the MGF because using the MGF here, in fact, would work. Perhaps you already know the punchline. The sum of geometrics is a negative binomial. Sorry, I maybe should have said spoiler alert. And this is actually very easy to show with the MGF, but here for practice, let's do it using the direct convolution method. Now we start with finding the PMF of S2, and then from there we're going to find the PMF of S3. So we apply the formula. Now just note that here the support of the geometric is 0, 1, 2, 3, so it's the non-negative integers. So here generically in our formulas we call this sum over all k's, but in the specific case at hand, all k's for which the probabilities are non-zero is to sum from 0 to x, where x here is the argument. Okay, so I want to find the probability that S2 takes the value little x. I'm going to sum for all my cases are going to be 0, 1, 2, 3, up to x. Well, yes, because here wouldn't make sense to have a negative value because probability that x is a negative value is 0. So it serves no purpose to sum those cases where the number here is negative because the probability would be 0 then. But likewise, we sum this, we stop the sum at little x. Well, yes, because here you see, if j were to exceed x, same thing would happen. We would have a negative value here. Imagine that j is bigger than x. This thing is negative, and the probability x2 equals a negative thing. Well, it's 0. So here we stop the sum at x. Other than that, it's not especially difficult calculations. Let's review them. The probability that the geometric takes the specific value little j is this, given here. If you don't know where this comes from, you can review your slides with the distributions, with the discrete distributions, or also your formula sheet. So it's over here. Okay, this is the simple expression for the PMF of a geometric with parameter p. Remember that q is just 1 minus p. Okay, so pq to the j, and then probability that x2 is also a geometric. So same thing, it's just that here we plug q to the power of x minus j. And you have nice simplifications, of course. Q to the j simplifies the q to the j over there. So you're left with this sum. And now realize in the sum, the index j is not present in this expression. So in fact, you're just summing a fixed number of time, a constant. You see, j is not present in this expression. So how many times are you summing this quantity p squared qx? Well, x plus 1 times, because you start the sum at 0, then 0, 1, 2, up to x. Okay, so you're summing p squared qx, x plus 1 times. This gives you the final answer. So this is an expression for the PMF of S2. Obviously, we're not done. The problem asks you to find the PMF of S3. So you apply the same technique, probability that S3 equals a specific X. Same thing, you're going to sum over all the cases. Now X3 equals J, and S2 equals X minus J, because obviously S3 is the sum of X3 plus S2. Okay, and then you just have a slightly more complex calculation, but they're not too bad, I believe. You write again, this is just the geometric PMF. And then what happens? Well, probability that S2 equals a specific X minus J, well, you use this expression over there. But careful, instead of plugging X, you plug X minus J. So X minus J plus 1, and P squared Q to the, not X, but X minus J, because this is what you have here, X minus J. Okay, and for the rest, there's a few simplifications. What is happening? Well, again, the Q to the J here is going to cancel the Q to the J over there. And you're left with this. Yeah, P times P squared is P to the 3. And then what else? Well, a few things you can put outside. So you see those things don't depend on J, so you can put them in front of the summation over here. And then what happens? Well, this thing, X plus 1, doesn't have any J in it. So here you're just summing X plus 1 times the quantity X plus 1. So you sum X plus 1 times the quantity X plus 1, you obtain X plus 1 squared. The other one, you need to be a bit more careful. This J here, you're summing, what are you summing? You're summing 0 plus 1 plus 2 plus blah, 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 up to X. There's a formula for this. It's simply X times X plus 1 divided by 2. Okay, this maybe you forgot, but yeah, I mean, it's just the case that 0 plus 1 plus 2 plus up to a certain value, in this case, X, where X is an integer, will be X plus 1 divided by 2. The kind of formula you see in high school, I suppose, and then you forget. Yeah, and so I believe we're almost done. There's just a few more simplifications here in this expression, because there's an X plus 1 here, there's an X plus 1 here. So the next page, we put the X plus 1 in front, because this is divided by 2. We're gonna have a 2 here that cancels out the 2. And then more simplification, there's a 2x here, so minus x, you just get x. Okay, and you're almost done. Now, this is a perfectly fine expression that is quite simplified for the PMF of S3, but now we would like to recognize that this is in fact the PMF of negative binomial with parameter 3. So this step here is just a bit of rewriting to highlight that this is a negative binomial 3P. Yeah, well, you just take a moment maybe to convince yourself that this thing is exactly the same thing as the combination here, right? Because I mean, we can do it actually. Let's not be lazy. This combination, you see, a combination you recall would be, well, here you have a 3 plus x minus 1. So in fact, you have 2 plus x. So it would be 2 plus x factorial divided by x factorial divided by well, 2 plus x minus x factorial, that's 2 factorial. But you see, 2 plus x factorial is 2 plus x times 1 plus x times x factorial, but then it cancels out with this one, so you can just forget about it, divided by 2. And of course, this matches the expression we have over here. And why do we write in this way? 3 plus x minus 1 is just to recognize that this is indeed the probability mass function of the negative binomial. Let's check our slides for week 0. Negative binomial. I've went too fast. It's here. Okay, probability that the negative binomial equals x is indeed the parameter key, k. In our case, that's 3 plus x minus 1 divided by x, and then blah, 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 p to the k, q to the x, which is indeed what we have with the parameter k equals to 3 for us. So indeed, S3 is a negative binomial 3p. Hopefully you agree. Okay, that was the example of the discrete case. Now we review the continuous case, but it's very analogous. Now, let me just take a sip. I'm losing my voice. Okay, sorry about that. Now assume, same thing, we want the distribution of S, that is the sum of two things for now, X plus Y. X plus Y are continuous, independent random variables. If they're continuous, we can write their density functions little fx and little fy. Then by analogy to the discrete case, those formulas, yes, those formulas, we simply replace the sum by integral, et voila, we have formulas we can use for free. Okay, those formulas that, forgive me, I'm not proving them really rigorously here, but I think you know that usually when we go from discrete to continuous, we just switch the sum by integral and it works. Okay, so integral of fx times fy s minus x, and that's for the density, and that's for the CDF. And the same trick applies if you know how to find the distribution of x1 plus x2, then you can find the distribution of x1 plus x2 plus x3, and then you find the distribution of x1 plus x2 plus x3 plus x4, and then blah, 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 up to you iterate as many times as you need to find the distribution of S being the sum of a generic number of random variables. To help us understand, we have an example here where we're going to find, it's a classical example, I suppose, showing using this method that the sum of two gammas, careful, two gammas here, but with the same lambda, the same rate parameter, it's again a gamma. Maybe you know this already, but let's review it. And again, it would be easier to use MGS, but for the sake of illustration, let's do it with the convolution method. So yeah, let's do it. X is a gamma, K. So careful, well, careful. We don't need the first parameter to be the same. So the first parameter of the gamma can be whatever, and then you sum Y with possibly a different parameter here. This would be the shape parameter. What needs to be the same is the lambda, the rate parameter. Okay, now show that then their sum is also a gamma and identify its relevant parameters. Now here they do help you by giving you the following integral. So they give this as a hint. If S, K, and L are all positive, then you can use that this integral, x to the k minus 1, blah, 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 is all expressed neatly in terms of in the gamma function. So this will be useful in a moment. Overall, the method is this. You use the formula over here, because indeed it gives you directly the density of the sum of two things. Okay, so you plug the density of one of the random variables and then the density of the other, but evaluate at s minus x. And then you integrate with respect to x. Okay, so in our case, we have the density of the first gamma. Then you have the density of the second, evaluated at s minus x. You replace this by the expressions. Take a moment to convince yourself those are the right expressions for the gamma. But again, careful that in the case of the second one, you evaluate at s minus x. Then hopefully there's some things that simplify. Why not put everything that is a constant that doesn't depend on the integration variable x here? Let's put it outside. So those things, you can put them outside. Same thing, lambda to the k, lambda to the k2. You can put this outside as lambda to the k1 plus k2. And what else? Well, this thing here, e to the minus lambda s, this doesn't depend on x, so you can also put it outside. And then, well, maybe I should keep the same color for, let's say that lambda is yellow. Then what remains, you see, is this integral. And then, well, you recognize that it's exactly the integral given in the hint. You see, the integral from 0 to something, 0 to s, of x to the something, s minus x to the something else. right? K minus 1. So in this case, K minus 1 is what is called K here, and then what is called L here is K2. Okay, so then you can just use the hint, and you're pretty much done. You see, because the result would be gamma K1, gamma K2, those things cancel those that are here, and then you're left with whatever this is. This is well, gamma in our case K1 plus K2, which is here. And then there's this other term, of course, that you should not forget, s to the K1 plus K2 minus 1 here. And then hopefully you see that indeed we have obtained the density of a gamma with which parameters? Well, lambda is the same as before, but then we have an updated shape parameter. It's K1 plus K2. Yes, indeed, this matches the density of a gamma with shape parameter here and rate parameter here. We've done it. Okay, now, of course, the hint here did a lot of heavy lifting for us. Maybe it would have been slightly hard to solve this integral without the hint. Okay, we're done already. So when I have fun, I don't see the time passing, but I believe this video is already pretty long. So I'll stop here. And there's going to be another video to wrap up the last section. So thanks so much for listening, and I'll see you in the next video. Bye-bye.